reaction involves using ultraviolet light to cleave the bond. This homolytic cleavage generates an oxygen-centered radical that abstracts a hydrogen atom from a remote, often, position, which is a key step in achieving selective functionalization of a molecule. The process yields a variety of products, and the reaction has been instrumental in the development of remote functionalization strategies. Mechanism of the Barton reaction. 1. Homolytic cleavage. When a nitrite ester is exposed to ultraviolet light, the nitrogen-oxygen single bond breaks homolytically, forming an alkoxyl radical and a nitric oxide radical. 2. Hydrogen abstraction. The alkoxyl radical abstracts a hydrogen atom from a carbon atom 5 positions away, hydrogen, a process facilitated by the formation of a stable 6-membered ring transition state. This creates a carbon radical on the substrate and regenerates an alcohol. 3. Radical recombination. The newly formed carbon radical and the nitric oxide radical then combine to form a nitroso intermediate. And 4. Further reactions. The resulting nitroso group can undergo further reactions. For example, it can tautomerize to form an oxime or can be further modified into other functional groups using standard organic chemistry techniques. Significance and applications. 1. Remote functionalization. The Barton reaction is a prime example of a remote functionalization technique, meaning it can introduce a functional group at a site that is far from the initial alcohol precursor. 2. Regioin-stereoselectivity. The favored 6-membered ring intermediate in the hydrogen abstraction step provides high regioin-stereoselectivity, making the reaction valuable for functionalizing complex molecules like steroids. And 3. Radical chemistry. This reaction relies on neutral radical chemistry, avoiding the need for ionic intermediates and allowing for selective activation of otherwise inert CH bonds.